Right. Starting a little bit early today compared to the time that I said I was going to start, but I am pretty tired. I'm probably not even going to make it through all of the puzzle tonight. But I did kind of want to get started and get through some of it at least. And I figured, why wait till 9 o'clock? It's not like, everybody's super punctual arriving on the dot and will be mad that I did stuff for 15 minutes anyway. So one thing to note is that the next puzzle coming up is 17, or we're going to do 18 today. It's not that I think 17 is particularly bad or anything like that. I just have some ideas in mind for 18 that I'm excited to explore, and I assume they'll, not actually make the problem easier. Like, every time I try to apply theory to a problem, it's like, well, yeah, this theory is great, but this is a tiny program. You could just do a dumb thing and it'll work. And the theory takes pages and pages. But it's theory I'm interested in, so we're gonna try to apply it. So a brief reminder, if you haven't read this problem before or seen me read it yesterday, the idea is we're basically building a binary tree with values only in the leaves. And the values in this case are numbers. So this is the pair indicator. Is like the pair indicator is the wrong word. The syntax for a pair, I guess, is just these brackets with a comma, and there's nested pairs, so that's why it's a tree. And basically the this is about like some addition problem where addition is a really, totally different operation from normal addition, where we operate on pairs. Basically, we're given. I mean, let's look at my input actually. Is it like a single number or two numbers? No. What is this? Every number is a pair. Here are some example numbers, one number per line. You can reduce it. Your homework assignment involves adding up a list of shellfish numbers. Snailfish numbers. So we're going to get a list of these pair things, and we have to interpret each as a number and kind of fold add addition over the list. And then we're going to do something to then we're going to do something to check that the result at the end is correct, which involves looking at magnitudes, which whatever. I'm not going to look up what a magnitude is right now. 3 times the magnitude of its left element, 3 times the magnitude of its right element, and the magnitude of the regular is just that number. Yeah, so it's some checksum you run over the whole tree that you're supposed to produce. Fine. And it's a fold L that we're doing. Not that it matters. I don't think we're going to get as far as doing fold today even. So the interesting part of this problem is basically like this. Detecting when you have a pair that is nested within 4 pairs, and then like also this explode operation is the main thing. And a pair or a number splitting is not terribly hard. I think the number just turns into 2 like other numbers. To split, you replace the number with a pair. Round down and round up. So easy, right? Yeah, so really the entire hard part of the problem is find places in this deeply nested structure where there is a pair that is contained within 4 pairs, and then do this weird operation where you take the left half of that most nested pair and add it to a different number that is nearby it in the structure, in that it's like the next number to the left. Pair's left values added to the first regular number to the left of the exploding pair. And I kind of want to like draw some diagrams to explain this stuff, but I don't have a good way to draw diagrams. So actually, maybe what I'll do is reuse some existing diagrams that are related to a thing that I'm going to talk about in a minute. The idea that I was excited about here. So we're going to be talking about zippers today. I guess Hewitt zippers. I don't really know what the other kind is called, but we're not using them. I didn't really want to zoom in that far, did I? Maybe I did. Anyway, so this uses kind of a similar... It happens to have a binary tree handy, which is all I need right now. So our input is a binary tree, and if we suppose that like, oh, this is a little weird because this tree has like some elements that have just one child. Let me I want to talk about what the next leftmost item in a tree is. So let's imagine this part of the tree doesn't really exist. It's just these 5 nodes in kind of the top leftish area. What is the number to the left, the nearest number to the left of this one? This is a leaf. We're pretending this stuff doesn't exist, so it must be a number. This is a pair, this is a pair, and these are numbers. So the nearest number to the left is this one. And I think, and so that would be, this would be written as like left bracket of 1, 2, right bracket 3, right bracket, right? And so indeed the 2 is the next one textually to the left, but also kind of to the left in this tree structure. So what does it mean to go left in this tree in general? I think that what it means is to look at the node that you're in and traverse upward until at some point you start traversing downward again, but I'm not sure exactly when that is. I had it a couple hours ago, I think. So there's a difference in a way between this node and this one, right? We're again pretending both of these are leaves. Well, no, because these are both kind of at the left end of their respective subtrees, right? We can't even really talk about what this guy's leftmost neighbor is. Is there a bigger tree we can look at? No. Okay, let's look for binary tree diagram. There you go. That should have some good ones. So here is a binary tree diagram. Get out of it. So if we're looking here, what's the number just to the... Wait, what? Oh no, I thought it was showing the wrong window. I'm not. Just I can only see part of what I'm broadcasting to. Anyway, it doesn't matter. So from here, we want to get to this node. Are you gonna get out of here? And from here, we want to get to this node. So there's some difference between 10 and 11. The structure of them. That means when we get to 5, if we're coming from 10, we keep going up. And if we're coming from 11, we start going down. And so I think it's basically, you want to get to the next leftmost number, you want to follow upward links until you follow one where the node you're coming from is the right child of the node you're going to, right? And then you start going, you go left once and then right as far as you can, basically, right? So if we follow that algorithm from here, we go up once, and the node we came from isn't to the right of the node we're at now, so we go up again. Now it is at the right of the node we came from, so we go left once, and then right as far as we can. We wind up here. We start at 11, we go up once, and the node we're coming from is the right of the node we're going to. We go left once, and then down right as far as we can, which is 0. It gets us here. I think this isn't, if we have this concept of up, right, and down through a tree, I think this accurately describes the way to get to the leaf that is closest on the left. And to get to the leaf that's closest on the right, of course, you do the opposite thing. Now, this diagram is not a tree we'll ever run into because we don't have any like nodes with just one child. So the question of like what to do from here is kind of ill-formed. That won't be part of our input. But so that's the algorithm I have in mind for understanding what is nearest to the left in a tree structure. Let's actually write that down before I forget it. To move left, to find the nearest left nearest leaf on the left. 1. Go up until you traverse backwards across a right child link. 2. Go left once. 3. Go right as far as you can. So I think this is an important algorithm. And we're gonna, I think, need the opposite as well, which is fine. We can just, because to explode a number, the right number is added the first regular one to the right, etc., if any. And then the entire exploding pair is turned into a regular number. So, I think this is going to be very important. And let's talk now about, well, before we get to talking about zippers, let's imagine, let's just define the data types that we're kind of going to want to use to represent this tree, right? We have a number, and we could parameterize it by a and then put ints in it, but I don't think there's much reason to. So we'll say a number is either a simple of int, or it is a pair of number and number, right? And this is fine. This is a great data structure. But it isn't really conducive to doing stuff like traveling up. There's no upward pointers, right? You can't say, what is the parent of this node? So to do this kind of explode thing, you would have to traverse down into a node that needs to explode, and like figuring out how it needs to explode is not that hard, but not super trivial. And then figuring out where it has to go, like it's horrible. What would you even do? So, you know, one thing you might try would be to keep track as you're descending into a node what set of turns you took. Oh, I want left and then right and then right and then left. Right? And then you could just make like some changes to that list somehow and traverse a different path and maybe find your way. You know, maybe you follow all those same instructions, but you don't follow the last one or the last chain of rights or something like that. And then you're at this node. That's like how you do part 1. You don't follow the last chain of rights or the last single right, I guess. And then you go left and you remember the directions you were following and so on, and you go right as far as you can. You arrive at a new place and you replace it, and like now you've got a new tree. But that's like really hard, right? But still, it's better than impossible, which is where you are if you don't have any way to like keep track of your path through the tree. But there's this really interesting concept called zippers that I don't know what language it was developed in or what context. I feel like it might be actually in Haskell that like this kind of thing was discovered. But I always found it kind of fascinating for a couple of reasons. So this is why I have the clickbait title about using calculus to implement arithmetic. So what might be even better than if we saved a set of directions from the root to our node, that's great. But every time you want to get somewhere, you have to go up to the root and then follow directions down. And like, you know, if this were a deep tree, that would be very expensive. And every time you want to add something, you have to add to the end of the list, which is also expensive. And so what might be even nicer is what if we had like a node like this, but also had a sort of breadcrumbs of how we could go back to the top from here, right? Instead of saying, oh, you know, from the root go right and then go left, I could say from here go up to a node of which you are the left child, and then go up to the root of which you are the right child. Something like that, right? Which by itself is not this big innovation. But what makes it cool is that if you do that, you no longer have to store the rest of the tree at all. You can encode the entire tree inside of the instructions for how to get back to the root. Instead of saying, oh, go back to the root, go back up to the right, and you'll find a node that you were the left child of, you can say, you can have the instructions be, you know, go up a level, and there should be a node there whose left child is the node you just came from, and whose right child is whatever, and whose path back to the root is whatever. And in that way, you can kind of reorient the tree to be centered or focused around the place where you are, so that it's easy to make local changes and navigate in the local area without having to copy the entire tree or anything. So this is what's called a zipper. It's kind of like a node and the enclosing tree kind of reoriented to be focused around the node. And it's a little like unclear how to think about it. Like what exactly information do you need to reconstruct the rest of the tree from where you are? It's hard to like be sure, right? And so this is where we get to the calculus, which I just find wild that this exists. But let's indulge ourselves here by writing down first, you know, what is the... Well, you know, actually, let's actually go ahead and replace these with A's for now. Number A, number A. Maybe we'll put the ints back later. But we can ask, how do you represent, how many values are there in this type's domain, the type of number of a, where a is some type variable? Well, we say let's say that n of a, or number of a, sure, is, well, it's however many there are in an a, because we can only, there's only one, no, there's one simple corresponding to each a. So we can add a to something. This is a sum type, right? We talk about sums and products. So there's a kinds of numbers that are just simples. And then how many pairs are there? Well, there's kind of a number a times a number a, right? And have I messed this up already? Not really. I don't think so. So that's fine. It's kind of like you don't know exactly how to. It's this weird equation that you would have to solve maybe to figure out how many number a's there are for a given a. But we can kind of say, what if we replaced what if we replaced all the number a's here with a variable? We could say that x, the size of our thing that we're looking for, is a plus x squared. Right? Seems okay. And now we're going to do a really weird thing, I think. Well, we'll say x of a squared, because x... well, isn't that what I just did? I'm still a little fuzzy on exactly what the formalisms for this are. But if we did that... Now, just for fun, just for fun, suppose we decided to... This is a polynomial. What if we decided to take the derivative of this polynomial with respect to a? Then we could say that x prime of a is equal to 1 plus, if you remember your calculus, 2 times x of a? X prime of a? I don't know exactly. Again, I'm a little fuzzy on the formalities. But it's x. Sure. I think x. Maybe I'm taking the derivative with respect to... Yeah, I don't remember the chain rule, honestly. But this is a derivative we could take. Why would we take the derivative of a type? It remains to be seen. So let's then say, well, what if we try to then reinterpret this formula as a data type, the same way we interpreted this data type as a formula? We could say, well, how could we construct a type that has 1 plus 2 times x of a values in it? Actually, I think this should be x prime. I don't know. So we could then say x prime, well, we could say number prime of a is, well, 1 is just unit. So let's say that. Or I guess we want this data nil. We'll call it nil. So that's just, there's only one value of type nil. Because when we took the derivative of a, we got 1. Or else there's maybe 2 x primes of a. So it's either a number prime... Hey, Rubik's. I said a while ago that I'm kind of tired and I'm not going to finish this whole thing, but I wanted to talk about zippers today. Are you familiar with zippers? You're like the most Haskell familiar of people in this chat, or people who are usually in this chat anyway. So you could say that nil or a number, number prime. Oh yeah, okay. So we're doing zippers. Are zippers and derivatives familiar to you? Because I would totally go over this again, because this is the entire exciting part of the today. Okay, you used a zipper. that's what we're doing here. I'm showing the derivation of zipper through through derivatives. How you can determine the zipper for a type based on the type's definition. We can say that like number A, we'll say number L for reasons which will become clear, of A, or number R of A. Yeah, zippers are related to derivatives. It's incredible. If you take a type that represents roughly a tree, and you kind of transform it into sums and products, like so, and you take the derivative of the formula you get, and then you turn that sum and product thing back into a data type, you get the zipper for that type. It's absolutely unbelievable. And so, okay, this is maybe, you know, we could clean this up a little bit. This is one way to make there be two number primes. Oh, this is actually supposed to be a number prime of A, I think. Is that right? Yeah, it's not two A's, but two X of A's. I think it's actually just supposed to be an ordinary number. I don't think it's supposed to be a number prime. And so we could encode this in a slightly better way, maybe by saying data dir equals L or R, and then we could say data number prime of A is nil or... No, these are supposed to be number primes. I remember, right? This is like number A. Something like this. So at each step, we're supposed to have a node, basically. And we're supposed to have like a linked list of these. And that should be what this represents. I've messed this up. Let's go look at the... I'm still fuzzy on all this stuff. Let's go look at this article on Wikibooks. Yeah, the kind of natural way, I mean, eventually what you get to, if you like do this right, is you say, oh, this is actually just a linked list of pairs of directions and numbers. Where you eventually get to is type numZipper is an A and a list of... No, it's a list of pair of A, number and direction, kind of, right? This is like the zipper that you can get to, and it's equivalent to what I'm supposed to be writing here, but I'm kind of fuzzy on what that is. And so there's a sort of confusing article on the Haskell Wikibooks that I barely understand. I've read it so many times. Yeah, so branch... Okay, but they haven't put in the A's yet. So here we have... Yeah, it stores a normal node as well as whatever data you would need there. Yes, so that type, data zipper is ZR of number and zipper. That is sort of isomorphic to a list of pairs of numbers and directions, right? If you look at it, and top is the kind of nil of the list, and the L and R parts are entries in the list with a link to the next part. And the contents of one of those is a number and a direction, basically. So eventually you can get to this as your zipper type from deriving this in a way that I'm sort of confused about. So it's supposed to save a... Okay, this wasn't supposed to be number prime, was it? Oh, it's supposed to look like, okay, we have a number of A and then a number prime of A as well. So that's where the pair comes from. Or where we get one element in the link. So as I said, I'm still not like super fluent in this stuff, which is why I got this wrong a couple times on the way there. But you can derive the zipper for a tree-ish type by taking that thing in the sums, converting sums and products, taking the derivative, and then going back to data types, which is like wild. So this is kind of like how we get here. And now I'm going to throw away the derivation. I don't know. It's kind of cool, right? We'll leave it in. We'll just comment it out. Oh, and we were actually going to make these just take ints. So I think, in principle, what you are supposed to do here would be take the derivative of this thing with respect to int, but it's very confusing to me to do that, because you have to know, does number have an int in it or not? Whereas if you have a type variable, it's very easy to take the derivative with respect to a type variable, because you can tell if it's there. So what I wanted to do first is just write some functions that are useful for a zipper. Let's say up. Up is a nice easy function. Up is a function from numZipper to maybe numZipper, because you might be at the top and it might be impossible to go up. I'm honestly not sure I'm even going to use up for anything, but I probably will. Oh yeah, that's true. I mean, I'll figure it out eventually. Who knows if I'm even going to compile anything tonight before I have to pass out and go to bed. So up of empty list is nothing. You can't go up if wait. Something doesn't seem quite right to me. Doesn't a numZipper need... This isn't a zipper. This is the num context. And a type of numZipper is a number and a num context, right? Because you have to have the node you're pointing at as well as the way to keep going. So up of n and the empty list, we must be at the root. At the root. Up of n and then I guess I need to get a cons here. P D parent and direction? No. And PD cons to path? Context? Equals case D of, if the direction is L, we must have come through the left child in the parent. So we're returning a new, these aren't, yeah, numZipper. So the new number that will be the one we're focusing on is pair of n, the node we came from, is being inserted on the left. And then I need to break apart the p, don't I? Pair. Can I... What is the pair? What is it a pair of? The left... It was kind of a pair with a hole in it, right? It didn't have a left child because... Yeah, I know it's a pair of numbers, but what numbers are they? One, I mean... XR... Oh, wait a minute. We don't have... Our num context has a number and a direction. And a number has two parts. And the left part is what we're supposed to be replacing with what we are. So is what was stored in the left the actual parent? So confused. I guess... It wasn't... I'm trying to read this and, like, go back to what I'm supposed to think about this. So if you get to a left, it has an x. Okay, so this is important, right? This x. No, x is the data at the node. We don't have an x, so that's not important. So R says... Right, because we don't have a whole number there. Is that right? We just have an A. Which for us is an int. I don't think I understand zippers still. But it is, it's storing a whole node. And their example, a node is like a tree. So, like, okay, when you're storing a turn left, you're saying you turned left, and there's a single node there, which is what you would have gotten if you had turned right. Basically. Right? And so in my case, I'm saying I'm looking up. Let's It would be kind of nice if I had an actual type for this. So what is the parent of my thing? So I have a pair. That's what a num zipper is. And there's a number on the left, which is the current node. And then a non-empty context. And we're looking at the first one, which is R, I guess. What you would have gotten if you had turned right. R. Okay, I'm just going to not try to split this into a single case match. I'm going to write multiple equations. So now we have one number. It's not a pair of numbers. It looked like a pair of numbers earlier because I was confused, but it's not. It's what you would have gotten if you had gone right. So we'll call this one L. This is what you did get when you went left. Now we can say it's number LR just number LR pair LR, I guess is what I called it. And then the rest of the context is just CTX, right? Yeah, that's not so hard, right? And if you go up with R, and the left child would have been this, you write the same thing here, pair LR context. Why did it look like it didn't want to compile that? Defined but not used N. Well, fine. So am I getting warnings about this? Yes, many patterns not matched. But actually, what patterns though? I'm not inspecting the number on the left at all. So it can't be that I'm not handling that. And the thing on the right, I'm handling it being empty, and I'm handling it being a non-empty list starting with R, and I'm handling it being a non-empty list starting with L. So I think that is total, unless one of my types isn't what I think it is. Yeah, I think this is correct. I don't know why... How do you turn on dash wall and... Oh, it didn't seem to mind that. Yeah, I'm not getting any warnings from GHCI. I think LSP is still just confused. Or confused again. And so, one thing we can do, is we could write a function like, is this a pair nested 4 deep? And that would just be to go up, 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 and see if you're, if you succeeded in doing so or not. Well, I agree, but like, it's claiming there are patterns not matched in LSP. And dash wall is agreeing with you and me and saying there are none. So I don't know why it thinks that's the case. But it's just LSP being rebellious as far as, unless you're disagreeing with it. So we could write a function like it needs exploding is a function from num zipper to bool. Right? And then we can say needs exploding of simple n anything is false. Simple numbers never need to explode. Needs exploding of pair something. Well, I mean, node as pair something something whatever is case up 4 times node of nothing, false, just anything, true. And we could use is just here, and I think that would be fine, probably better. But we need to say where up 4 times is up, and like what the heck is the monadic composition function? Is it like this? We have to import that from control monad, I guess. I've already forgot that I typed it with right arrows, okay. So that does compile. This type checks. So I think this up 4 times thing is probably looking pretty hot. And so now we have a function that, given a focused location in a tree, tells us, does this location need exploding? And so one of the things that I think we need, well, let's write left and right as well, because these are important traversal functions. Yeah, I always forget though whether like the right arrow version of this and the left arrow version of this both exist, and they're like flipped versions of each other. And I never remember which one like takes the which function first. In this case, it doesn't matter because functions are the same, so I get away with it. But let's say we wanted to implement left is a function from numZipper to maybe numZipper. And we can say left of simple anything is nothing. You can't go left from a simple node, right? And left of pair LR context is just of L. We're now looking at L. And our context needs a new pair of number and direction added to it, which I guess is R const to context. It type checks. Incredible. So now we can replace those lefts with rights and say it's just R L L. And this compiles. So now we've got some nice, simple navigation functions for walking around inside of a zipper of numbers. The trick is that I've written only the easy functions. There are a couple of hard ones that I don't have a very solid grasp on how to write. Because I think that what I need functions next and previous, which iterate over the tree kind of in text order, I guess you could say, right? We're looking at, well, maybe this is a better thing to look at. We have to, it talks about the leftmost value that could explode. The leftmost pair explodes, right? So we have to be able to iterate over the tree in left to right order. And find the first place that qualifies for exploding. And to do that, we need basically a next function that goes from some node to the next node in left to right order. And I kind of thought through what this was going to be this morning, but I've had like a long day, and I didn't have it very clear in my head at the time even. So I think the idea is it needs to be pre-order, because we need to look at the pair before we look at either of the numbers inside of it, because the pair itself is what needs to explode. So once you're looking at a pair, what comes next? Well, its left subtree comes next. When you're looking at a simple, what comes next? Well, you have to look up and determine whether you got here from the left, in which case go right, or got here from the right, in which case go up, I think. You know, maybe that's not as complicated as I thought it was. I think that describes a left to right traversal. So, we're going to define next as a function from numZipper to maybe numZipper. Next of a pair LR context is, thank you Rubix for double checking me, because it took me 25 minutes to figure that out this morning away from the keyboard. So oh, actually I guess I was at the keyboard in the sense that I was like in bed watching YouTube and like half awake, but I wasn't typing anything. So right, we're looking at a pair, and the next node needs to be a zipper looking at, I gotta stop using these tuples, by the way, I hate them. Looking at L, that's the next node. Just. I said that if you came from the right, you have to go up, but that's not quite true. You have to keep going up until you get to a node that you came to from the left. That is a little bit trickier. Just L of, oh my god, my brain is like falling off. I guess I need to make a new zipper here, which means I'm consing a pair. No. I'm consing a tuple of R and R onto context, saying when you get back here, you're going to go right. Next of L and RR context, just as we did in up, is going to be, we're just going to look at R, right? We've seen L and we've seen its parent because that's how we got there, right? Hang on, is this right? This doesn't look right. This should only be if L is a simple. Well, okay, we've already handled all pair cases, so everything down here is a simple. Yeah. we're looking at a simple, and there must be an R, which is what we would have gotten if we turned right instead. And so we need to just say, yes, go look at that node, please. R of LL context. Now, when there's an L in the context, because we're looking at... Wait. Am I... do I have my L's and R's backwards in all of this? Because I'm saying if I'm looking at an L node, and there's a right node in the tree, this should be R, or L, right? It should be I went left. Here, I went right. And L is what I would have gotten if I'd gone left instead. And likewise here, this left should have an L. And this right should have an R, saying I went right. Here's what I would have gotten if I'd gone left. Okay, so if we're looking at an L, and it has an L, which we can tell it's an L because it's got an L direction in it, then we say, okay, look at the right node, in fact, and then say, oh, and if you'd gone left instead, here's what you'd be looking at. Okay. Now, the interesting one is if you go next of R, and there's an L and an R direction here, I think at this point, because there might not be a next, but there can only ever not be a next if we just went right, because that would be the very rightmost node in the tree that has no next. So we have to be like case matching something at some point here. So if we looked at, I think we need to scrutinize context some more. Because if context is empty, then we're trying to find the rightmost node, and we got to the root of the tree, and so there's like nothing there, right? So I think we write case context of empty, nothing. So this seems right. And if it is a left, if you could have gone left, but instead you went right, then we have to do something weird. Let's leave that case for later. If, however, you did go left, you got here from the left, obviously I can write context prime here, but if I'm looking at a node, and that node is the right child of something, and the parent of my current node is a left child of something, what does that mean? I think it means I want to go into the right child of my parent, right? Yeah. But I feel like I'm making this too complicated. Can't I just say... like, next on something at this point? No, I guess not. I went left. Okay, so... oh, I have too many R's in scope now as well. You know what actually might be helpful is if I give these slightly different names. We're looking at a right child. Ugh, no, I can't even figure out what name to put there. We... I don't know. I think I'm gonna go to bed. This is like I need more focus than I have right now to write this stuff. But I'm glad I could at least enlighten you, Rubik's, about derivatives. You might check out like also the derivative of oh, I'm trying to remember. There's some weird thing like if you take the derivative of AST for a regular expression, you wind up with a function that parses it. That doesn't sound right. There's some way in which regular expressions are also related to derivatives of data types. Regular expression derivative algebraic data type. Algebra and calculus of algebraic data types. That's not really what I wanted. I don't think. I mean, it does actually talk about this. Anyway, there's stuff about like a one-hole context, which is not what we're doing. It's a kind of different flavor of zipper, I think. Today's problem is tough, huh? I'm trying to find differentiation regular expression. Haskell? Regex calculus? Oh, this sounds good. Yeah, here we go. This is kind of cool. I don't think this is the article I originally read, but derivatives of regular expressions, which describes how to directly convert a regular expression to a DFA without going through an NFA. And anyway, so they define a regex type somewhere. Here, I guess. It's one of a class or... and okay, whatever. Anyway, so I don't know. But it's a thing you might research if you're interested. We'll have a look at what tomorrow, or the most recent problem is, and I can commiserate with you guys before I give up and go to bed. Beacon scanner. Okay. Dump some stuff into the water. They float motionless and maintain the same position. Detecting all beacons in a large cube A scanner detects beacons nearby within a kind of square style radius of 1,000. Beacons that are most 1,000 units away have their precise positions determined relative to the scanner. Okay, so we're told how close each scanner is to every beacon it can see. Yeah, 2020 day 2 part 2, or day 20 part 2 was the one part I didn't do last year. I didn't like that puzzle at all. That was the jigsaw puzzle one, right? Scanners don't know their own position. Region can be constructed by finding pairs of scanners overlapping detection regions so that there's at least 12 beacons that both scanners detect within the overlap. Scanner 0 sees this. 1 sees this. They don't know their rotation or facing direction. Oh, I do want to throw up. Even just like doing this in 2 dimensions without rotations is too hard for me. I don't want to do this either. I do want to finish the zipper thing eventually because it is an area that interests me, and implementing my own zipper for a type is cool, and doing something with it. Writing functions that operate on it. Oh my god, yeah. I sympathize with you not wanting to do this. Assemble the full map of beacons. Okay, so what is this about 12 then? Absolute position will be expressed relative to scanner 0. So by finding pairs of scanners that both see at least 12 of the same beacon. I don't understand why 12. Is that because of the number of degrees of freedom in rotations? Yeah, each scanner could be in any one of 24 different orientations. And then somehow half of those orientations are double counted when you're looking at a pair of 2 of them together. I just assume 12 of them is somehow enough to figure out your relative orientations to each other. Yeah, like I'm not gonna do this day this year. That's what it looks like to me. But I'm certainly not doing it tonight because, like I said at the beginning of the stream, I had a long day and I need to go to bed. And we're just not gonna finish the zipper thing tonight. I'll try to get to it later. Maybe some off camera. Although I think I'm pretty busy. I don't know. We'll see. Anyway, that's about all the words I can put together out of my mouth today before I go to sleep. So hope you guys enjoyed. little lesson on zippers, even though it was pretty fumbled in a number of places. Go take derivatives of some data types on your own and see what cool stuff you come up with, I guess. Right? Using this kind of structure. It's kind of cool. Anyway, yeah, that's it. Thanks for watching, and I'll see you next time.